I'm going to explain how you can detect and label objects in images using small models you can run on your laptop. I'll then show you how to annotate your own dataset and use it to fine-tune a model that is specialized for your application. Not only will you be able to detect objects, you'll generate bounding boxes or outlines that describe their exact position within the image. This is useful for many applications, for example, detecting players in a soccer match, finding patterns within medical images, or even finding recyclables within an image of general waste. If you're relatively new to vision models, I'll explain everything here step by step. Whereas if you're more advanced, I'll still include some tips to get the very best performance. And there will be 4 parts to this video. First of all, I'll talk through Florence 2. This is a really small multimodal model that is capable not just of detecting objects, but also giving you bounding boxes or outlines. It's small enough to run on your CPU with decent inference as well. So I'll describe the mechanics of that model. Then I'll show you a free notebook, a Colab notebook. It's based on a Hugging Face notebook where I'll show you some inference. You can run this on your CPU. I'm going to run it in Colab, and I'll show examples of detecting objects, creating bounding boxes for them, and even segmenting, providing a detailed outline of specific objects. Then I'll move on to work for fine-tuning, which will involve a custom dataset. I'm going to fine-tune on chess pieces. So I'll train the model to detect the chess pieces within an image. And I'll show you a tool I've developed that allows you to annotate images. So if you just have raw images with objects, you can very quickly annotate them using this tool. I'm going to do it for chess pieces. And then I'll move on to the fine-tuning notebook, where I'll use that dataset to do the fine-tuning, and you'll see that the performance radically improves. It's actually quite poor on the chess pieces before I do any fine-tuning, but it's quite good afterwards. Just a quick shout out to Andrew Walsh. You can check out his Medium profile here. He's the one who gave me the tip to check out Florence 2. And when I did, I was really surprised with the quality of the results given how small it is. So that led me to dig deeper and find out about bounding box fine-tuning. So Florence 2, it's a model by Microsoft. And as the 2 suggests, it's the 2nd edition of the model. Let's take a quick look here at Hugging Face. You can see there are actually 2 versions of this model. There's kind of a large one. It's not very large though, called Florence Large. And then there's a smaller one called Florence 2-Base. You can see in the files that it's really not a big model. That's a PyTorch model of 1.5 gigabytes in size. And if we look at the base model here, we can see how big that one is. It's about 500 megabytes, so half a gigabyte. We're going to look at the base model in the free Colab notebook, and for fine-tuning later, I'll fine-tune the larger model. Now, this model is multimodal, so it takes in images and it takes in text, and it combines that information then to provide captions, or to provide captions and bounding boxes, or captions and the pixels around the image, which is segmentation information. Just one other note on the models here. While there's Florence 2 Base and Florence 2 Large, there's also a fine-tuned version, which you can get just by appending, I think it's -FT onto the model. So I've done that here. Yeah, and this is a fine-tuned one. So they have the base model, and then they do some instruction fine-tuning, and probably you want to use the fine-tuned model to get the best performance. Now, all of the instructions around inference are described here on the model card. Basically, there are specific tags you need to provide depending on the use case. So if you want a simple caption, you'll provide between these angled brackets, you'll put the word caption in caps. Then you can get a detailed caption. You can get bounding boxes. I'm going to show you all of this when we move to the notebook. But just before we take a look at the notebook here, I want to explain very briefly how this model works behind the scenes. So as I said, it takes in images and it takes in text. And these separately go through 2 encoders. So there's an encoder for the image pixels. So the image is described by a series of pixels. The pixels each represent a number, are represented by a number for red, green, and blue. So that RGB, red, green, blue information for each pixel is provided to a vision encoder. And that converts, it actually transforms. First, there's an embeddings layer that will convert it into vectors. And then those vectors are transformed in an abstract space to give output encoded vectors representing the image. And likewise, any text you provide in, which in this case for Florence 2 is going to be some tag, which might say caption, or it might say provide bounding boxes, just some kind of a tag. And then sometimes you will input text as well. For example, you might ask the image to provide bounding boxes for a certain thing. So you might say, I want bounding boxes for a dog. And so dog will be some text that you'll append in addition to that little flag that tells it to give you bounding boxes. So this input text will go through a text encoder. It'll be embedded and then it will be transformed in vector space. And the outputs of the vision encoder and the text encoder will go through a decoder, which will produce the next predicted token. So if you're trying to caption an image of a dog, you're asking, well, what's the caption for this dog image? So it should respond with something like, let's say, a Labrador. So the first predicted token might just be the word a. And then that is fed back around because this is auto-regressively generating next token. So that first token generated, which would be a, is passed back into the decoder and it will generate the next predicted token, which would be Labrador. So it's still an autoregressive model, but it's an autoregressive model that has encoded information coming from images and from text. Now, just a quick side note, if you've looked at the video on Pixtral or Lava, some of these other vision models, or Moondream, for example, or Malmo is a more recent one, the architecture is a little bit different. Recently, with, say, GPT-type models, GPT-3 and onwards, it's common not to have an encoder. You just use a decoder. And the decoder architecture, for example, in Pixtral is a Mistral Nemo language model. And so in this case here, there is no encoder for the input text. You just use the decoder itself in order to transform the vectors. So basically the encoder here has been thrown out. And there are arguments for and against using the encoder. The encoder can be specialized to deal with special input tokens, like saying generate captions versus generate bounding boxes. Whereas the decoder, if you've no encoder, the decoder has to be more general and cater to inputs that are both recycled and original inputs that might have specific commands within them. So either way, this is a bit of a side note, but Florence 2, one of the key things is it does include an encoder for the input tokens, and that feeds the decoder, whereas in a lot of the multimodal models from my other videos on Pixtral, on Lava, on Moondream, there is no encoder. You're just feeding directly the embeddings in to the decoder. Now, I'll just briefly describe the vision encoder. So here within Florence 2, you have some kind of vision encoder. Generally, how these work is by splitting up the image into patches, then converting the pixel information, the RGB plus the patch position through embeddings to get to vectors, because you always want to represent your information as vectors. And then you have some kind of vision transformer. It might include convolution, it might include attention, to get a transformed representation of the embeddings that is then fed into the decoder. Now, there's a question here of how do you get a model to provide you with information on bounding boxes or on the segmentation, that's the outline of a specific object. And the way that we do this, or we indicate to the model that we want different tasks, is by using these special inputs. And there's actually a wide variety for Florence 2. There's probably over 10 or maybe 12. I'll go through them in detail, but the main three ones are caption, just to generate a caption, dense region caption, this should be all caps, where it'll give you back a caption like a Labrador, but also it'll tell you the bounding box for the Labrador. And then there's referring expression segmentation, where you can input dog and it will provide you with the outline, the polygon outline of the Labrador. So these are the three main tasks, although there are a variety of tasks that build from this and go in the other direction, say from region to polygon or polygon to region or caption to bounding box versus bounding box to caption. So there's a whole variety that Florence 2 supports, but these are the three main categories. And the way that coordinates are described is on a normalized basis. So no matter what image you put in, no matter what aspect ratio you have, the X, the width and the height are always going to be normalized. And so if I have, say, 300 pixels, the 150th pixel here will have an X dimension of 500 because it's normalized to between 0 and 999. So 500 would be here. Likewise in the Y direction, and note that we're coming down from the top left. We're going to be working between 0 and 1000 or 0 and 999 on a normalized basis. So just for example here, you always represent the coordinates as for a box as x1. So let me actually just fix the capitalization and actually draw a box here. So I'll go to a shape, and I want to draw this box, which is 250, 125. So 250 is going to be 1/4 of the way across, and 125 is 1/8 of the way down. So I'm going to start my bounding box here, and then I'm going to do 750 across, which is 3/4 of the way, and 750 down, 3/4 of the way down. So that there is the box that represents these coordinates: 250, 125, 750, 750. Let me just quickly empty the box so there's no fill, and let me make it a little bit larger so that we can see it. Okay, so this is the bounding box here, and it represents 250, 125, which is the top left coordinate, and then 750, 750, which is the bottom right coordinate. So you can see this is how we're going to represent the coordinates. And actually, each of these coordinates, when it comes as the output from the LLM, is going to be represented with a special token for each of these possible values from 0 to 999. And they're going to be represented with tokens that looks like this. So it'll be LOC underscore, and then the position. And actually, there's no commas used, and then LOC underscore the position. And here again, we'll have LOC position, and then lastly, LOC and position. So this is ultimately how the model is going to output coordinates for a bounding box. And we'll see this when we get to the fine tuning, but I just wanted to show you for now that we use the convention of X going from the top left and Y from the top left, which is the same, I think, as a NumPy array. And then we normalize the width and the height on the basis of 0 to 1000. And so that's my quick overview of the Florence model. I'm going to show you now how we can inference the model on some generic images, and then I'll show you how we fine tune for a chess data set. Just one note in advance of when we get to fine tuning later, we're not going to update all of the parameters of the model. So there are about I'm not sure how many billion parameters, but there's 0.5 gigabyte worth of parameters. We're not going to fine tune them all. We're only going to fine tune what are called low rank adapters. That means if we have a large matrix, we're going to attach a temporary matrix, and that temporary matrix will be a lot smaller in size. And we're going to adjust those weights instead while freezing the main weights. And then at the end, we will merge those adapted weights onto the base model in order to generate an updated model. This is called low rank fine tuning. It means instead of updating every single dimension of every matrix, we only update some of the high level key dimensions instead. That's maybe an abstract way to think about it. So with that, I'll move on and show you how we can inference these models just on a GPU or in a Colab notebook. I'm in the Colab notebook now, and I'll put a link to this in the description. We're going to connect to a GPU here. You can just run it on a CPU. It, I think, will be quite slow on a CPU from Colab, but if you're running on your Mac, for example, or you're running on a Windows PC, you can get inference. You can get a response within maybe 10 seconds is my experience. Maybe a half if you set the device to MPS, which is something I'll maybe show you down below. So we're connected here, and I'm going to install Torch Vision, Torch Audio. Actually, this isn't probably necessary within Colab because these are already pre-installed. But if you're going to run locally, you will need to install those. We do now want to install transformers, INOPS, TIM, and TQDM. Actually, I'm not entirely sure if TQDM is required. TIM is definitely required. We're going to install HF transfer, which is a fast weights download. The weights are quite small, so it's not absolutely critical. And this is the environment variable to set if you want fast download using the Rust library from HF transfer. Now, after running some imports, and these are the checks to see if MPS is available. This is relevant if you're running on a Mac. If you set the device to MPS instead of CUDA, you'll get a speed up versus just using your GPU on Mac. That's if you have an M1 chip, M2, M3, those more modern chips. So the model we're going to load is Florence, and we'll load the base model, which is just 500 megabytes in size. Here you can manually set the device if you want. You could set it to CPU rather, but it will default to CUDA if it's available, or otherwise it will default to the Mac MPS. So here we're going to load the model, and we're also going to load the processor. So we have the model, auto model for causal, and the processor. We do need to trust remote code, which means running scripts from the hub. That comes with risks, so you always want to make sure you're using a legit repo. We are, because we're using one from Microsoft. And we're going to set the data type to automatic, which should set it, I think, to float 16 if we're in Colab using a T4, or bfloat 16 if you're running on a CPU that supports bfloat 16. So I'll run that, and we're going to start downloading the model here. In the meantime, we can go on and define a function called run example. Now, what this does is it will take in a task prompt and text input. The task prompt is that angled brackets input that indicates what task we want the model to do. And the text input is some kind of command if the task prompt supports it. So if you want a bounding box for a dog, you're going to have to put in the input text of dog. So there's going to be a text input. If you're just asking for a caption, on the other hand, you're only going to have a task prompt that says object description, OD, if you just want a caption, or say caption within angled brackets, and there's no text input required or allowed, in fact, in that case. Then we'll set up the processor, which you can think of as a tokenizer that does tokenization both for the images and for the text. We're going to set up the inputs, which are a combination of input IDs from text and the pixel values. And then we'll run model.generate on the inputs and pixel values to get some outputs from the model here. So I think we can run this. When we print model device, we should see CUDA. Yeah, that's correct. And let's just take a quick look at an image. So the image that is provided by the model providers is this image of a car that we're going to detect in various ways. And now we'll start to run some prompts. The first one, we'll just get a straightforward caption, and it should take 1 to 2 seconds on CUDA. Okay, 2.65, and it gets a green car parked in front of a yellow building, which is correct. Now you can get a more detailed caption, and you can get a detailed caption and a more detailed caption. So this should be a paragraph, although in this case, it's not any longer than just the detailed caption. But these are both correct in line with the image. OD is object description. So this is a command you can run to get back some bounding boxes. And you can see here, it's providing back the bounding boxes for the image, which is exactly what we want. But furthermore, for each bounding box, it's giving us a label. So OD gives us both labels for the object and the positions. So it's giving us the car and 2 different wheels. Now, to visualize these results a bit better, we can define a function that will take the bounding boxes and overlay them on an image. And likewise, when we generate a polygon, we can create a function that will show us that polygon outline overlaid on the image. So here we're defining the bounding box, and then we're plotting it for the image using the results from the object detection. And you can see it works really well. This is a small model, 0.5 GB, and it's pulling out the car and the wheels. Now, this is the image that's provided in the repo, so you can expect that it's an example that will work well. But still, I've used it on some different images, and it seems to work pretty broadly. You'll see it's a bit weak on the chess pieces, but with fine tuning, we can rectify that. You can try out also dense region caption. This looks for any dense colored regions and will label and caption them. So we can run that, and we can plot it. So yeah, it's picking out the same pretty much dense regions here. And you can also ask it to propose regions, which, yeah, you can see here it's proposing a few different regions that might correspond to objects of interest. You can also provide a caption like dog and ask it, say, a green car parked in front of a yellow building. Let's actually try this one here. And it's providing some bounding boxes for the green car and the yellow building. So it's basically pulling out the key phrases from the text we provided and pulling out those objects. So lots of examples here. One more I'll show you, which is the referring expression segmentation. Here we're going to feed in a green car as a piece of text. We're going to feed in this task prompt here and see if it can generate a polygon for the car. And we have a function that allows us to draw out a polygon, draw polygons, and do so in a way that we can overlay on the image. And here we go. Just in a few seconds, it's got a polygon that describes the shape of the car. And you could say maybe it's a little bit rough around the edges here, but broadly speaking, this is really good in terms of the object detection. There's one more function you can run here. I keep saying that. I'll just quickly note that this involves giving in a bounding box and then getting back a segmented object. So we've passed in a bounding box here. You can see with the location, that's about 70% across the image, 50% down. So that's like somewhere here. And then the bottom right is, let's say 7/8 across and 3/4 down. So we're asking for an object within this region here. And indeed, it's picking out the wheel. So this is working really well. As I mentioned, it'll be a bit slower on CPU, maybe 6 seconds on Mac, maybe 12 seconds on CPU, but pretty great and really low in terms of the total size of the model. So the question now is, can we test out the performance on more difficult data sets that it may not be familiar with? I'm going to take a look at the chess data set. This is something that I use pretty much across all of my videos. It's the chess. If you just go to, this is actually the bounding boxes data set, but if you go to chess pieces, you can find an image plus caption data set I've generated of, say, a single white rook, one chess piece, namely a rook. So this is a simple data set that we can use for fine tuning on chess. And I'm going to show you a version of this that's annotated for bounding boxes, just like I showed here. So we'll have the boxes for a given image, and then we'll have the labels for each box. So say a white rook or a wooden chessboard, and that's for this image right here. And now we get to the question of how we can fine tune the model on a custom data set. And for this, we're going to need to annotate a data set, because if you already have images, even if you have captions, you're going to need now to have bounding boxes for each object that's within the image. So I'm going to go through a program I have generated to make or to annotate a data set, which simply means adding bounding boxes to images you have. And then I'll show you how to walk through a fine-tuning script. I'll be working out of the advanced vision repository. You can check it out if you go to trellis.com/advanced-vision. And this is where you can purchase access to lifetime access to the repository, which includes very many scripts. It now includes ways to fine-tune Flux, fine-tune Pixtral, Llama. So you've got all the multi-modal models, including now fine-tuning for bounding boxes. So I'm going to clone this repository into VS Code or Cursor, and I'm going to work out of the fine-tuning folder, fine-tuning and then Florence 2. But actually that's for the fine-tuning scripts. And first I'm going to do some data preparation. So I'm going to work out of the data prep folder and out of the scripts folder within data prep. So let me just increase a little bit my screen size here. And you'll see I'm already in the scripts folder where there's this script here called bounding box annotation. And what this allows you to do is take any data set that's on the hub that has images. So first you'll want to create a data set with images. You can do that by checking out my video on Lava fine tuning, where I use the create Hugging Face data set. And previously I even create captions for those images. You don't need image captions, you just need the images. So I'm going to start off with the chess pieces data set, this one here. And all you need is this images column here. And we'll take those images, download them, and then we will start to annotate. So I'm in the scripts folder and I'm going to run python bb annotation.py. And this is going to get me started with an application right here where I'm able to load up a data set from Hugging Face. So I've got trellis chess pieces up here, and the column that has the images is called image. So I need to have that correct here. And I'll just click on load, and this is going to load up the data set. Now, it will take maybe a few moments. I've pre-downloaded it, so it looks very fast, but it can take a few moments to download the data set. And it's going to download the train split, which is called train, and then the test split, which is called test. And you can see I have 3 images in the test split, and I've got 48 in the train split. And I'm able to navigate through these different images. I can do that just sorry, it's asked me for a label first. I can do it using the arrows on my keyboard early as well, which you'll find handy. And the way that we'll annotate this is by putting in labels. So here I'll put in a white rook. Sorry if my screen is a bit small, I don't have a way to increase, but I said my white rook here. And then I just drag over this and that enters it in. Now what I recommend doing is if you have a lot of repeated objects, just type in the label once here and then navigate to the next image, which may have the same one. So then you can very quickly just go through like this and find the images that have got a white rook. So I'm navigating all 48 of them here, just checking for a white rook. Let's see if I have any more. Yeah. So here, put in this one here, this one here. Yeah. So you're going to go on and do this for all of them. And of course, you're going to do all of the pieces. So I'll do it for a white pawn as well, like this. And I'll go through and do it for a white pawn. Now, at any point, you can click on Save Annotations, and you can also load up annotations. So I'm going to load up some annotations I've saved from earlier, just called ChessBB. And now you can see I've got everything annotated. So I've, whoops, if you click on the white space, it'll accidentally annotate that. So you can see here, I've annotated absolutely everything. In some cases, I've even provided an annotation for the chessboard. Let's see if I can find an example of that. If I go all the way back to, yeah, so here you've got the rook, but I've also annotated the chessboard. And I've set this up so that if you select an area that goes off the image, it will just apply the very edge of the image coordinate. So don't worry about overlapping too far on the side. And once I have this, I can just click on export to hub. So I'll type in my dataset name. So it'll be trellis, chess, bounding boxes. And if I click export to hub, it's going to ask me for a token, a Hugging Face token. I'll enter that in. And then it'll take a few moments and start to upload this dataset to hub. And when it's uploaded to hub, it should look something like I have here. Let's see. I am on chess pieces and I want bounding boxes. So it will have uploaded a dataset with the image, with the boxes, and then with the labels for those boxes. And this is exactly what we need for when we're going to do fine tuning. Now, with that done, I'm going to move to the fine tuning step. And maybe I should just say a few quick things about how the dataset is generated. These boxes here are normalized dimensions. So let me just stop that reloading. So these are not just the pixel dimensions when I click on them. They're normalized to the image width. So you can see here for the white rook, it says 322. This is not pixel 322 across. It's 322 divided by 1000 multiplied by the width, because these are all normalized dimensions. So just wanted to note that. The next step rather is for us to fine tune using this data. And to do that, I'm going to make use of a notebook, which is present within the fine tuning folder. So instead of data prep, I'm going to move into fine tuning, and I'm going to make use of the script in Florence 2, which is just called trellis Florence. This is the fine tuning script here. And we're going to run through this, load the data, and I'll show you some of the fine tuning to get some nice results where we're able to get some reasonable annotations or some reasonable bounding boxes for this chess set piece. So to get started for fine tuning, as per usual, I'm going to go to the one-click LLMs repository is a public repo where the name suggests some one-click templates for LLMs. I'm going to use RunPod, and I'm going to start up gigabytes of VRAM if you wanted. But just for speed, I'm going to use an A40. It'll just take about 2 or 3 minutes to fine tune on that. Deploy. Now, once that's started up, click connect, and then head over to the Jupyter Notebook. And then I'll upload Trellis Notebook and start here, a short install and pip install Trellis. If you want to have an assistant that allows you to, you'll just, if you're in RunPod, you will need to do the install here. And I'll leave some details on that. You can find the install instructions on PyPy, installs involving transformers. We're going to need PEFT, that's parameter efficient fine tuning. It's parameter efficient because it uses low rank representations of the matrices for if you want logging, TIM, requests. And I'm going to log into Hugging Face so that I'm able to push HF transfer. And then I'm going to load up the model, and you can load the smaller model. Sorry, by the way, so I've got my screen size increased, and yeah, so we've loaded up the large model. Because I'm on a GPU that supports bfloat16, I'm going to use that. Use float16 if you're on T4 or Colab. You could optionally quantize as well if you want to save VRAM, but this is a small model. So we're going to load the model. We're going to load with flash attention, and we're going to load the processor as well. And we'll print out the model configuration here if you're interested. what we'll see is that it has a vision model, and then it has a text encoder and a text decoder. So you can see some details on the configuration here. You can also see the full model details, like here's the vision tower. It's actually really big, so it takes up a lot of notebook space. But right at the bottom, you can see there's the language model, and it's got an encoder, and it's also got a decoder. And the encoder is a transformer. It's got some attention, like here, and some linear layers. And the same in the decoder, it's got attention, and it's got linear layers, which are right here. So that'll be relevant when it comes to applying the LoRA adapters. We're going to apply the LoRA adapters to the linear layers and train those adapters instead of training all of the layers or all of the weights in the layers. So next, we're going to set up some of the same functions we did in the inference. We'll set up a function to plot bounding boxes. Let me just check I have run that model. I'm actually going to just reload it now because I earlier fine-tuned the model. So we will define a function as well for plotting polygons, although we're going to focus on bounding box training. We'll define the run example function as I showed earlier. This is a slightly modified version where you can input a task prompt and it's going to automatically then generate a bounding box if it's relevant to the task or a polygon if it's relevant to the task. So let's take a look. Here I've got categorized all of the different types of inference you can do. So there's caption, detailed caption, more detailed caption. Then you can input a region and get out a description of that region. So this requires, there's an optional text input for this, where you can say, for example, top right. So let's actually run that one. We can say region to category, and let's get whatever is in the top right of the image. So if I run that, you can see the top right is a door, which makes sense. So that's the region input. Then there's region to description, which converts region to description. Bounding box response. So there's a few options here. You can get object description, dense region caption, or a region proposal. Then there's text input and bounding box response. So here you're putting in a caption and it will take pieces from that and try to generate the correct regions. So here it's picked out a turquoise car, brown doors and brown doors. And that's working really nicely actually right there. Polygon segmentation response. So here you can input, say, a car, and it should output the car. So that's good. It's generating a polygon. We like to see that. Then region segmentation I showed earlier. And there's also open vocabulary detection, which will give bounding boxes and polygons. So this is a very general approach, and it should give polygons and bounding boxes. In this case, it's giving polygons actually, but it's not robustly giving bounding boxes. So not working entirely robustly in this case here. Okay, in any case, we want to focus on fine tuning. So let's move on. And by the way, I should mention there's also OCR. So you can do optical character recognition, including with regions. And you can do that on, say, a newspaper and get the text out of it. So yeah, it's really a very versatile model. All right, so we're going to load now the dataset trellis chess bounding boxes. And we're going to get the model to provide dense region caption. So here it's going to provide a caption and it's going to provide the bounding boxes. So let's load that data set. And I've created some functions to visualize the data set and check that the bounding boxes are actually correct. So what this does is it takes the normalized bounding boxes and calculates the actual pixel bounding boxes based on the actual image width and the image height. So we can run that function definition. And here we've got a visualization. So it's just applying my bounding boxes from the data set. You can see that's correct. You can see that's correct. You can see that's correct, a wooden chessboard. So always good to visualize the data. And you can see exactly the format here. If you look at the raw output of the model, it should be generating the caption, then the location, XY, XY of the top left, bottom right of the box. Then if there's another caption, it should generate top left, bottom right. And I notice actually there's a small space here that is not quite correct. And that can probably be fixed if I, it's the join function here. There shouldn't actually be a space between the join functions. I fix that later on, but either way, this is looking good. And we've got the data being generated for a given representation of that data. So next we want to see, okay, by the way, that was not running inference. That was literally just plotting the bounding boxes of the data. Now we're going to run inference and we'll see how good or bad the model is. So we'll pass in the detailed caption and we'll run this on our data set and take a look how it performs on the test split. So you can see it's quite poor. It's just identifying wooden pieces and giving the full photo as the bounding box. So yeah, there's a lot of room for improvement here in all the cases. Okay, here it does pick out a chess piece, but it doesn't quite label it as the correct chess piece. So let's see how much better we can do. And for that, we're going to need to set up a training loop. So for the training loop, we need to have a little bit of familiarity with how the processor works, which takes in the raw images and text and converts it into vectors that are then tensors that are then used within the training. Just a note that you can look and inspect the tokenizer. This is what converts the text into tokens. You can inspect it and inspect the token IDs. So it's got a beginning of sequence token of 0 and an end of sequence token of 2. If you want to look at those tokens and how they look, you can just take away the ID part and you can see it's actually the llama 2 or llama 2 type of S for begin and /S for end. We can also take a look at how the processor works just by tokenizing kind of a dummy batch, just one row of data with the text test, and then opened image is just one of the images above. So if you do that, you can see that when the processor processes this raw data, it outputs a tensor for input IDs. This is the text information, and then pixel values. So there's a tensor also for the pixels. So this is what the processor does because these are then fed in to the model for doing a forward pass. Now, what we need to do is we need to set up, using a data collator, we need to set up our inputs and our outputs. The outputs are actually going to be called labels. So we need to define the inputs, which will be just images, and then the outputs, which are going to be a list of the objects followed by the locations of the bounding boxes. So we're going to iterate through each of our examples. And for the input text, we're going to just have a prompt that is equal to the task prompt. And the task prompt in our case is going to be a detailed region caption. Let me just double check exactly the quote. Yeah, it's going to be just detailed caption. So that's the task prompt we're using. Actually, let me just double check because I think I define a global variable here when I load the examples. Yeah, sorry, we're actually going to use dense region caption. So this is the task prompt that we're going to train for. You could train for other task prompts either, but this one here outputs objects and then the boxes. So this is what we're going to go for. So the prompt that we feed in is going to be that. The image is just going to be the image from each row. Then we're going to get the caption and we will get the caption from the data set. Now, sorry, there's one further thing I should say here, which is this is just a standard data collator, which is going to be if you want to fine tune on captions only. That's why I'm getting the caption and the prompt. But actually, we want to fine tune on outputs of not just labels, but bounding boxes. So we're going to take a look at a bounding box data collator. So this one here, it's going to be quite similar. We're going to have the task prompt appended as the prompt. We're going to append the images. There's no change there. But the caption is going to be a full caption that includes the bounding box sizes. And that's built up here. And the way that works is by cycling through the examples, checking the boxes. And then for every box, it's going to append the label for that box and then the X1, Y1, X2, Y2 location. And then it will concatenate for each box, it will concatenate these. So you'll have a series of label for locations, label for locations. And that's what I call the full caption. And that full caption is going to serve as the labels. Now you need to process the inputs separately to the outputs. So here we're processing the inputs, which consists of the prompts, which is just the task prompts, the images. And then we're also going to process the outputs, which will be called labels. And these are going to be the captions or the full captions and nothing else. There's no images in the outputs, of course. And then we're going to return here the input IDs. We're going to return the pixel values and we're going to return the labels. And we're also going to return an attention mask. The attention mask will just ensure that the model is only able to look backwards at the inputs and not able to cheat by looking forwards. And with that, we'll define the data collator as the bounding box data collator. which is going to prepare our data. Now, I will show you, it'll be a bit more intuitive when you see the data here. I'm going to just inspect a batch of data that I put through a given data collator. So let's print out some examples. So here I've got sample number 1 with 2 boxes, a box for a white rook and a wooden chessboard, and then one for a white rook and a wooden chessboard. Actually, these 2 examples look very similar. It's just the rook is in a different position. And you can see the process batch structure. It's got input IDs, attention mask. These have to be the same size, of course. Pixel values, labels. And if we just decode that into human readable form, you can see the input is actually looking like this. So it says locate the objects in the image with their descriptions. Now, where did that phrase come from? Well, actually, when we pass in these angled brackets, so if we pass in any of these task prompts here, actually, these are not being input to the LLM. They are being converted to a string that's predefined, and that string is being tokenized. So that's an intermediate step, but it's all handled by the processor. So that's why when we inspect the outputs in human readable form down here, actually, I've just input the dense region caption, and that's being converted into a string that says locate the objects within the image. It's got a beginning of sequence token appended by the processor, an end of sequence token appended. And then the target text, which is the label, is exactly the caption I provided, followed by the locations. Then the caption for the second box, followed by the locations. And the processor is automatically adding an end of sequence token and a beginning of sequence token here. Okay, so we're happy now we've processed the data into a format that we can feed into the trainer. And that format, by the way, needs to be here. It needs to be an object with input IDs, attention mask, pixel values, and labels. That's what the trainer will expect. Now, we're not going to train all the weights, so we're going to generate some adapters instead to train. And for that, we'll use LoRA, low rank adapters. We'll use a rank of 32. That should be enough for some detail. The LoRA alpha, I like to set based on the size of the model. It should be larger for larger models, smaller for smaller models. Broadly speaking, I think it should be roughly the square root of the inner dimension. This is because if you used a rank that was equal to the inner dimension, you should end up with having a learning rate that is just the learning rate you would use for the full model. Sorry, I realize that's kind of advanced what I'm saying, but if you look at my video on LoRA fine-tuning, there's also actually a live stream. You can find out more details on why I recommend that choice. I do use RS LoRA. This means that the speed at which we train will depend on the rank. If you have a smaller rank, you're training in lower dimensions, which means you can move faster. That's why RS LoRA, well, not why, but RS LoRA aims to allow you to train faster with a smaller rank, which is good because you converge more quickly. Now, we need to decide where we're going to apply the adapters. And when I say where, I mean where within that large model structure are we going to apply adapters? And the answer is we're going to apply them to all of the linear layers. So any of the attention like Q proj, O proj, V proj, the linear layers like fully connected 1, fully connected 2, that's where we're going to apply them. We could list out the modules if we wanted, something like this here. We could do Q proj, we could do O proj, but a much quicker way is just to train them all by doing all linear. Optionally, you can train the embeddings, but we're not using any new tokens. We're not introducing any new tokens, so I don't see a need to train the embeddings in this case. Okay, LoRA dropout means we'll randomly drop out some weights in some of the, I think it's forward passes, maybe backward passes. And what that does is it avoids overfitting. All right, so with that, we're going to apply LoRA to the model, and we're going to figure out how many trainable parameters we have. The number should be much smaller than the total parameters because we're just training the adapters. So yeah, out of the parameters of which there are 800 million, so there's 850 million parameters in this large model. It's really not that large. And we're only going to train 31 million of them, which is about 4%. Okay, so next we're going to move to the trainer, and we're going to decide to train at a learning rate of 3e-4. The smaller the model, the faster you can train it. So yeah, if you're around 1 billion parameters, probably you can train at 3e-4, maybe even 1e-3, you could try it. And we're going to train for 1 epoch at a constant learning rate. This is my favorite way to train. Just do constant learning rate. And at the end, do a little more training where you slowly reduce, or rather quickly reduce the learning rate. That's called annealing. So actually we're going to run it for 1 epoch at constant, and then we'll anneal for 1 epoch as well. So it's going to look like this. And the annealing is nice because if you look at the optimization space, we're kind of very quickly moving towards the local minimum, or hopefully global minimum of the optimization curve. And because we're moving very fast, maybe we kind of overshoot, but with this annealing phase, we're able to very slowly kind of settle down right into the very global minimum, hopefully. So that's the intuition of why you like to go constant to move fast. You want to move fast towards the minimum, and then you want to slowly settle into kind of that little nook or cranny that gives the absolute optimum. We're going to train with a batch size of 1 because we don't have that much data, and we do want it to pay attention to each sample individually as opposed to a more average sense. This kind of leads to more overfitting, but it also can lead to better information transmission. So I'll name the run here, and we're going to use a standard training argument setup. That's training arguments from Hugging Face. And what should I highlight here? I've probably called this the wrong thing. This should really be called Florence chess if we want to push it up to hub. We'll use gradient checkpointing to save on VRAM. Probably not essential because we have a lot of memory. And then we will set up the trainer, passing in the model, the training arguments, the data collator from earlier, the training data set, and the eval dating set. And now we can run. So it should take maybe about 1 minute to train. We're going to train a constant learning rate here, and we should see the training loss fall and the validation loss fall as well. Now, the validation loss may not fall all that much because it's going to be a hard data set to fit and it may be a bit noisy, but we can always see how the results look. So let me run this training and then evaluation, and then I'll do the annealing, and then I'll run evaluation again, just so you can see how that performs. It looks like it's going well though. It's, going down. Maybe that's a bump upwards there towards the end. So let's take a quick look. Running on those samples. And remember how bad this was before training. It was just giving a bounding box for the full image. So now it's getting the pieces, and it's also getting the colors. So that's good. Again, it's getting the colors. It's getting one of the pieces. And here it's getting one of the pieces, and it's getting all of the colors. So that's pretty good. Now let's do some annealing. So I'm just going to run for 1 epoch of annealing. By the way, 1 epoch, normally you anneal only for maybe 5% of the data set. But since we've very little data, I'm going to anneal for the full data set. Oops. So we're going to run that again. Now, if you want to get really good results, you should have more than 48 data samples. It's impressive how good you can get just with this few samples, but you should probably have at least 100 or 1,000 rows of data if you want to get really good performance. And in that case, you can definitely just train for 1 epoch and then anneal maybe for 10% of an epoch. So here I'll run the trainer, and once that's done, I'll run the evaluation. Now, while that's running, you can optionally then push the model to hub. If you do, that will just push the adapters because we're training LoRA adapters. So if you want to push a merged model, you should run merge and unload, and then you can push to hub with model.push to hub. And you should probably also push processor.push to hub just to make sure that you have the processor, so you have everything you need when you want to inference that model later. So here we're coming to the end of training, and notice how, the validation losses is falling throughout. It did kind of bump up when we started, which is interesting. I don't have great intuition for why that is. But when we look here at the evaluation, we've got the colors correct. One of the pieces is correct. We've got 2 pieces correct. And this one is almost correct. It thinks it's a pawn, but it's a bishop. This is correct. This is correct. So yeah, we're getting more than half of the pieces right now. And that's just with 48 rows of data. So you can see that this model is possible to fine tune really effectively. If you do push, you need to make sure that you're logged in to Hugging Face. So yeah, make sure that you've input your token with Hugging Face login. You can always log in by doing import. You can do from Hugging Face hub, import login, and then you can just run login like this. So if you do something like that, you can enter your token here, log in, and then you can run these commands to push if you want. So I'll just put that up here and I'll save this latest version. so that you all have, those who have lifetime access to the repo can run the fine tuning. And that's my overview of how to fine tune a vision model that can generate not just object descriptions, but also bounding box descriptions, i.e. where the objects are within the image. Now, the data annotation tool I showed you, that can be used pretty much for any model that you want to fine tune for this purpose. But when you fine tune the model, that will depend exactly on the syntax the model uses. And what I went through is just for the Florence 2 model. I'll put a link below to the Colab notebook. I'll also put a link to the Florence 2 paper if you're interested in learning more. It's a really powerful model that's very versatile. And then I'll put a link if you want to purchase lifetime access to the advanced vision repo, which now contains the scripts here for doing the data annotation and for fine tuning Florence. With that, let me know any questions below in the comments. Cheers, folks.